Okay, so I think we should get started. It's my pleasure this week to introduce Harriet Lau. She's an assistant professor at Brown, and she is also the CIG Distinguished Speaker. So Harriet is a geodynamicist with really broad interests that span all the way from the deep mantle to Earth's surface and the response of the mantle to deglaciation, but also changes in sea level. She did her undergraduate at Imperial College London before doing a PhD at Harvard with Jerry Mitrovica. She stayed at Harvard for her postdoc and then spent some time at UC Berkeley as an assistant professor before ending being at Brown, where she is now. So we're looking forward to hearing your talk and welcome.
Thank you. Thanks for the introduction, and thank you everybody for being here. It is like kind of talking during coffee. It is a tough time of semester to kind of carve out time, so I appreciate you guys for all being here. As Ben mentioned, I will be talking about how the solid Earth interacts with the cryosphere. So I'll be exploring this in the context of the mid-Pleistocene transition, and so this work is very much in progress. So I'm happy to welcome feedback, and I do have a thick skin, so good and bad feedback is appreciated. But what I mean by solid Earth dynamics is a specific process called glacial isostatic adjustment. And so under the load of an ice sheet, the lithosphere, so here this tectonic plate, here's my pointer, tectonic plate, and the mantle beneath, they will warp downwards, causing subsidence of the crust. And so this reduction of the ice sheet, so the reverse of growing an ice sheet will drive return flow. And so the crust will rebound as the mantle fills that pressure void. And so this can involve both elastic and viscous responses. And so it's very time scale dependent. And so we see this happening today. This is in response to the last glacial maximum. So 21,000 years ago, New Jersey was probably covered in ice. But around 7,000 years ago, the Laurentide ice sheet completely disappeared. And yet, this is Scandinavia. The Scandinavian ice sheet completely disappeared. And what you see is uplift today for an ice sheet that completely vanished 7,000 years ago. The same you see in North America. So Canada always moving to higher places, of course, as we move downwards. But this uplift that's happening today, again, is in response to something that completely vanished 7,000 years ago. And the fact that we're seeing rebound today is because of that sluggish viscous flow of the mantle. And so the delay of that deformation, we'll learn, is somewhat important in the story of kind of the Pleistocene ice ages. And so the Pleistocene is really defined by the appearance of Northern Hemisphere ice some 2.5 million years ago. And by Northern Hemisphere ice, I mean this kind of configuration here. So we have that Laurentide ice sheet, and we have the Fennoscandian ice sheet and much of Siberia covered in ice, and still present today, the Greenland ice sheet. And this is perhaps what ice cover looked like 21,000 years ago at the peak of the last ice age, sorry. But if you go further back in time, we can start to see patterns in the history of Pleistocene ice. And so one of the most powerful proxies we use to kind of infer ice volume that you might have come across are the oxygen isotopes. And these are found in marine sediment cores, measured in kind of benthic foraminiferous, so kind of shells like hang around the sea floor. And this is perhaps the most famous figure depicting a stack of many of these kind of marine sediment cores together by Lorraine Lasique and Maureen Raymer. And what you just see are variations in delta 18O within these sediment cores. And so low delta 18O, which is weirdly at the top, are times of kind of what we call interglacial, so in between the ice ages, and these dips below, are ice ages. And so if we take a look at some of the notable features, here we are today, and this is the last glacial maximum. And so the deglaciation from that point to today, you can't see it here, but it wasn't steady. It's full of different types of events, like meltwater pulses, and I'm just advertising my students' talk at AGU on that, on a specific event, meltwater pulse 1A. 14,000 years ago, sea level rose globally by about 20 meters in less than 500 years. So that's pretty dramatic. So again, this deglaciation was not steady at all. And the lead up to this last glacial maximum came around 120,000 years ago. This is the last interglacial. And again, it's steadier, but by no means steady, right? And so that's basically the last kind of cycle of no ice to the ice age to today. And it's characterized by this classic sawtooth pattern of steady growth and rapid decline. And so these zigzags are essentially signs of the Earth's climate, again, flipping between ice ages and interglacials. And so ice sheets in the Northern Hemisphere, as I've mentioned before, nucleated around 2.5 million years ago. And this is basically the mark of the Pleistocene. And what you see across the Pleistocene is an increasing amplitude in these ice ages as we move towards the present. And so, you know, I'm not sure I need to convince this audience as to the importance of kind of understanding climate and Earth's climate, but I guess, and so, you know, this phrase, I guess, is somewhat cliched, but the distinction I kind of want to emphasize here is the importance of considering the Earth as an entire system and its interacting subsystems. And so just because of my own bias, here's one example of where the solid Earth plays a role in how we understand climate. And so, for example, the Pliocene, so that's a period of time around 3 to 5 million years ago. Similar tectonic kind of arrangements to today, and similar CO2 content in the atmosphere. And yet, from kind of paleo shoreline data, sea level could have been anywhere between 15 to 60 meters higher than today, right? And so that, you know, is pretty problematic because we kind of think about the Pliocene as a proxy for where we might be heading, whether that's true or not. But that would make my hometown Manchester a beach town, which I wouldn't mind, but it would make my new home of Rhode Island definitely underwater, right? And so we need to understand this, but to understand this takes a component of what sea level's doing, but also the solid Earth beneath, right? And so this is one example where understanding the deformation of the solid Earth is key to interpreting these paleo shorelines that seem to indicate we're heading to pretty high waters, right? And so I do remember as a young graduate student in my group, there was a lot of talk about these kind of famous Pliocene shorelines. And I actually got to visit one. This is the Orangeburg Scarp that I think actually it's New Jersey as well. And here it is. It's that little kink in the road. And, you know, as someone who doesn't do field geology, this really doesn't inspire me to do field geology. And so I actually use this to inspire geologists to turn to the dark side and to kind of the modeling and the theory side of things. But, you know, in this talk, I'm going to discuss another example of that, of these kinds of interactions. Flip, here it is. So these ice ages are often described and connected with Milankovitch cycles, which I will discuss in a few moments, but as an enthusiast of like the history of science, I thought I'd take this time to put Milankovitch into a little bit of context because we just passed his 100-year anniversary of when he published his seminal ideas. And so what did Milankovitch do? He proposed that orbital changes result in changes in how Earth receives radiation from the sun, and that these changes could drive climate change. And he formulated much of these ideas as a prisoner of war in 1914. And so, you know, I do think about, you know, I think all of us have spent time in shelter in place and kind of thinking what I spent my time as a prisoner of my apartment in Oakland. That is British sarcasm there. I use the word prisoner very generously, but I honestly just watched way too much soccer. It was not nearly as kind of prolific as Milankovitch was. But prior to that, he actually just got married. And this is a quote from his journal after he was released, right? So after the war, upon his return to Belgrade, this is what he said: after a comfortable 3-day cruise down the river Danube, I arrived to Belgrade on March 15, 1919, thus completing my exciting 5-year wedding trip. So even after being a prisoner of war for so long, that kind of dark Eastern European humor didn't leave Milankovitch. But after he was released, he published all these ideas in this work that I won't even try to pronounce. But the important point I wanted to make here is that Milankovitch's ideas predated any core data. And so he continued to develop these ideas after he left and throughout the early 20th century. And you see a lot of these kind of these discussions documented in these letters where actually they describe conversations that involve kind of what I like to call gentleman trash talk, where he kind of dismisses ideas in that kind of like very like polite but brutal way that people did in the olden times. But what these letters show was that Milankovitch had a very difficult time publishing these ideas. And ultimately, I wanted to kind of highlight this as kind of more to highlight different means of the kind of scientific process, I guess, because, as a theoretician myself, it's easy to propose ideas, and actually Catherine and I talked about them. It's harder to show that they're true, right? And so this is a problem that Milankovitch faced, even though it's something we kind of, just accept today. Nevertheless, attempts were made to make use of Milankovitch's ideas. And so this slide is a culmination of several hours of like Wikipedia / other kind of like rabbit holing into early 20th century loess studies of the Baltic region. So loesses are basically windswept deposits, and amongst the kind of 1920s Germanic and Baltic loess stratigraphers, there was actually a lot of potential seen in Milankovitch's ideas. And actually, the earliest attempts of chronostratigraphy, so a practice that underpins paleoclimate today, involved loess stratigraphers using Milankovitch's Ice Age calendars to calibrate what they called their environmental phases. That's pretty cool. But finally, perhaps 15 years after Milankovitch's death, the classic Hazetal paper came out showing that strong correlation between the Ice Age frequency content from core data and Earth's orbital cycles. And so, now Milankovitch theory really lays the framework for much of paleoclimate in how you try to understand climate feedbacks, right? And so, this finally happened only 15 years after Milankovitch's death. So what are these orbital changes? So from low frequency to high frequency, these are the eccentricities, so how eccentric the Earth's orbit is. And that varies every 100,000 years. There is a longer periodicity as well. Earth's obliquity is just how much Earth's axis is tilted, so it controls the strength of the seasons. And that varies around 40,000 years. And then Earth's precession, which is this. So Earth's kind of doing this also. And that's 25,000 years. And so within the context of the oxygen isotope record and Milankovitch cycles, there are several mysteries that, or conundrums. And so the first is how these orbital cycles actually drive ice ages. And so I use drive a little bit generously there. So these orbital variations are extremely slight. And so the resulting changes in Earth's insolation are also very slight. And yet, in these kind of oxygen isotope records, we're flipping in and out of ice ages. So there has to be kind of really large positive feedbacks within Earth's system to kind of move these tiny changes to kind of big climatic variations. And perhaps what's even more puzzling is that if you look at the frequency content of ice volume in, say, the last million years, so this is a time series of that delta 18O, but just cut short, you see that the largest signal comes in the eccentricity band. And yet, if you look at changes in insulation that would drive these changes, supposedly, there's barely any signal in the eccentricity band, and except most of the power is elsewhere. And so that's the first conundrum. While these dramatic ice ages seem to be paced at the eccentricity period, the Milankovitch cycles actually show very little power in that period in terms of how the orbital cycles vary or change insulation. So the second conundrum, and this is going further back into the early Pleistocene, is that if we focus here in the early Pleistocene, the ice ages were dominated by the 40,000 year cycle, so that obliquity cycle. Until mysteriously switching to that eccentricity cycle we saw in the last slide. And so nothing about the Milankovitch cycles has changed, and yet Earth's response to this has. And so this transition is now what we call the mid-Pleistocene transition and the focus of much of the talk. And so accompanied by this was this general cooling and increase in the amplitude of these ice ages. And so this is shown a bit more clearly here in this figure. So this is going back, several million years, but what you see is the contribution to the signal from each of these cyclicities. So precession is very low in all of them. Obliquities varies, but it's significant throughout this whole time. But the real change here is this kind of amping up of the eccentricity cycle. And so around here is what we call this mid-Pleistocene transition. And so there have been several proposed mechanisms. So these from several people. So Peter Heuber suggests that these cycles actually just represent a beating between the eccentricity and the precession, the obliquity of the precession. And so the 100 years is kind of an average of 20s and 40s, basically. Changes in ocean sea ice dynamics have been suggested, changes from terrestrial to marine-based margins. Regolith removal, this is kind of in vogue, I'd like to think. It's basically as the ice sheet first grew, the Laurentide ice sheet grows, what that does is it scours the regolith, right? And so you're kind of changing the bottom boundary layer of what the ice sits on, and that could drive the mid-Pleistocene transition. When you read papers and you wish they were your idea, that's one of them for me. But there are interesting things about the geology, very much across North America, that might hint at the erosion history not quite matching what these models require. So all that to say is that it's not by no means and there's not an agreed solution to the mid-Pleistocene transition. And so the final conundrum that I'll discuss is the asymmetry in the rates of ice growth and decline within any single ice age cycle. So the ice ages over the last million years, as I said, are characterized by that sawtooth pattern where you have slow growth, rapid decline. And this was not always the case across the entire Pleistocene. And so what you see here is the rate of deglaciation and glaciation. And so as you see, moving from 2.5 million years ago to present, these track until towards the last million years, they start to diverge, where deglaciation exceeds rates of glaciation. And so that's the next thing I'll talk about. And so to summarize these conundrums, first we have how changes in insulation, these really minor changes in insulation can change climate in dramatic ways. We have what caused the transition between the obliquity and the eccentricity dominated ice age cycles, or what drove the mid-Pleistocene transition. And also what's causing this kind of growth in asymmetry of ice growth and decline over the Pleistocene. And so what I'd like to discuss in this context is really what the role of the solid Earth is in each of these factors. And so first a very simple primer on ice physics, and this is as sophisticated as it gets for me. But you can define an equilibrium line or surface. This is shown schematically here. If you are at altitudes above this line, precipitation will fall as snow and you grow an ice sheet. And below you're in the melting zone, right, where ablation happens. And so the growth of an ice sheet can be determined by changing the position of that equilibrium line. So if we pretend this schematic represents the Arctic, the northern hemisphere, we have the Arctic Ocean here. The equilibrium line shifts between the seasons, right? So in the summer, it's in a configuration where you just never form an ice sheet on land. Whereas in the winter, you shift it and you start to grow ice over the winter. So that's one way you can change the state of ice growth. You can move the equilibrium line. The other way to determine the presence of ice is rather than moving the equilibrium line, you can move relative to it, right? And so the presence of ice could be changed if you change your altitude, like shown here. And so what the solid Earth does, as I mentioned at the start of this talk, is that under the load of the ice sheet, the crust subsides. And so unloading, the crust rebounds. And so you're basically moving that ice sheet relative to that equilibrium line. Is this the right way? And so here's where the importance of viscosity comes in. Remember, I began that talk with these kind of GPS measurements of uplift that's happening today, even though we don't have an ice sheet melting. It's because viscous stresses in the mantle delay that response. Okay. And so what geophysicists that model glacial isostatic adjustment do is that we think of the Earth as a viscoelastic solid. We're very simple people. This is the Earth's mantle here. And so this is the simplest kind of viscoelastic model known as a Maxwell solid. It's a spring in series of a dashpot of viscosity eta, right? And so eta here will be the symbol for viscosity throughout this talk. And so viscosity is really just a measure of a fluid's resistance to flow. So high viscosity fluids will flow slowly, like the mantle, which really creeps. And so you can imagine applying a stress to this contraption, and depending how slow or fast you apply that stress, either the spring or the dashpot accommodates that stress and strains in response to that. And so to model GIA, what we really need to do is know how these properties, the spring constant and the viscosity, vary within the mantle. And so that time scale of rebound, or what I'll use now as relaxation, that kind of return flow of the mantle, really depends on the ratio of these two properties, just because of their dimensions. So we have viscosity in Pascal seconds and the elastic constant in pascals. And so the time scale of that relaxation depends on eta over k here. And because viscosity changes way more than the spring constant, it's really dictated by viscosity. And so more specifically, to address these conundrums, I'm really going to ask what GIA, glacial isostatic adjustment, plays, how GIA contributes to each of these processes. Okay. All right, so the first conundrum, why do we have ice ages paced at a 100,000 year cycle? And this was a kind of a high profile paper that came out now 10 years ago. Abiuchi and her colleagues, what they did was they kind of coupled an ice sheet model and climate model to address this question. And they were able to reproduce these kind of 100,000 year ice cycles. And I've just pulled a line directly from this paper, and it's here. This result supports the idea that the crucial mechanism for the 100,000 year cycles is the delayed glacial isostatic rebound. So even in all the things they were factoring in for a full climate model and a full ice dynamics model, what they actually found, it was GIA that controlled or enabled their 100,000 year ice cycles. And the reason why is that, during what happens in their model is that during the late Pleistocene, hit a state of climate. We're in this kind of generally cooling climate where you're in a state that allows ice growth of these major northern hemisphere ice sheets. And in their coupled ice sheet climate model, if they remove that delay, again, what they'd have instead was a protracted ice age. You wouldn't get ice ages that end every 100,000 years. You just have a constant ice age, which would doom us to, I don't know, maybe we'd be around, I don't know. But it would be pretty bad. And so the reason behind this is as you move to this cold enough state where ice grows, you still have these Milankovitch cycles growing, but the crust subsides. And once these Milankovitch cycles kick you back into a melt phase, what the delayed uplift provides is that as you slightly melt the ice, you're not rebounding to colder altitudes. You're staying low and staying at warm altitudes. And so the melting is enhanced so that you don't get this kind of permanent ice age state. And so they modeled this bedrock elevation here with this differential equation, where B is bedrock elevation, and they used a relaxation timescale tau here of about 5,000 years, which is not at all unreasonable. But just to give you an idea of what this looks like schematically, this is the process, right? So here's our ice equilibrium line, and we're reaching a state where we can start growing ice. And so we steadily grow this ice sheet, and the mantle flows and the crust subsides. And so once we hit an orbital state where we begin to melt, if the Earth was completely elastic, this would just rebound in phase. And you'd keep the ice sheet high, except that we're keeping the ice sheets low, and we're right now beneath that ice equilibrium line, and so you get enhanced melt. And so ice is kept at warmer altitudes, and this is the state we get. And so this is where we're at today. We're still uplifting in kind of the Hudson Bay area. Okay. And I just wanted to say that this idea isn't new. Abiyuchi, she really brought this kind of to the state of the art by using very kind of highly sophisticated models. The idea of bedrock elevation being something that is important in ice sheet dynamics has been around since, at least to my knowledge, at least the late 70s, where, you know, classic glaciologists like David Pollard, wouldn't like to be called classic now, and Ullmans, they proposed these ideas, which with albeit much simpler models because of the time, but produced similar results. And so this is the kind of differential equation that Pollard used, where again we have this bedrock elevation connected to a viscosity or a time scale of deformation. And so I hope that these two studies have convinced you at least that crustal subsidence is an important factor of this kind of 100,000 year late Pleistocene ice age cycle. What I'd like to just explore is how the same process might play a role in that mid-Pleistocene transition. So this is the second conundrum. And so now returning to Abiyuchi's differential equation of how she modeled the subsidence of bedrock, looking at this as a geophysicist, this kind of single timescale just doesn't sit well. The only way you can get a single value of tau is if the mantle is isoviscous, if the mantle has one single viscosity. And so the results I'm going to share with you today are based on two very simple, well-established ideas in geophysics, and that is larger surface loads, in our case ice sheets, sense deeper parts of the mantle, or their deformation penetrates the deeper parts of the mantle. And the second is that mantle's viscosity, eta here, increases with depth. And so the result of these two very simple ideas is that tau r, that relaxation timescale of how the ice sheet, the mantle flows once the ice sheet disappears, that changes with differing ice sheet sizes. And so that first point, if we take the simplest geometry, you know, an infinite half space that you would have done in class, if we have an ice sheet of length scale lambda, it will induce deformation that scales with lambda, because that's the independent limit scale here. And so with this bigger ice sheet, larger lambda, you'll have deeper penetration of deformation. The second point is that the mantle's viscosity increases with depth. And so I know this just from stories, but apparently the mantle viscosity world was quite a treacherous world as a researcher. I've heard of very vitriolic AGU sessions about mantle viscosity. Who would have thought people cared about this so much? But apparently it was quite vitriolic. And the reason why was that there were two camps. And this was kind of the view as of early 2000s, but this view stretched back to the 70s. And that was that some people thought the mantle was near isoviscous. And so what I'm showing you here is the surface down to the core mantle boundary. So this is basically the mantle. And on the x-axis is viscosity. And this is 10 to the 18, sorry, it's really small, to 10 to the 24 Pascal seconds. So this is orders of magnitudes in variation. And there are the green kind of profiles that people had inferred show a much larger increase with depth. And so this is kind of where the two camps sat. And in 2015, that kind of dichotomy lingered. But what we tried to do was use the same data set that inferred these isoviscous profiles, but we actually took one of the datums, specifically the geoid signal, and corrected it for kind of the latest ideas in what we think contemporaneous ice melt was, because we only knew this from having many years of satellite data to tell us how ice was melting, because that contaminates this geoid signal that is crucial to the deep mantle viscosity signature. And so when you do that, you end up with a mantle viscosity profile that increases by orders of magnitude 1 or 2 with depth. And so that's kind of where the fields converge. These are other independent studies. This is a viscosity profile derived from flow experiments, albeit, these are performed at pressures and temperatures that are more representative of the upper mantle. But if you kind of scale these results to the deep mantle, you would expect an increase in viscosity. Here's another study that actually focused more on seismic data and geodetic constraints, and again, kind of inferred a viscosity jump across the mantle of 2 to 3 orders of magnitude. So we're basically at this point where it's pretty well established that viscosity increases dramatically with depth. And so given that convergence, what we'd like to ask here is, how does that relaxation timescale we've been talking about then change if we no longer are thinking about the mantle as an isoviscous mantle? And so we're going to do some very simple experiments to calculate this. First, we're going to take that viscosity profile I showed you earlier, and we're just going to take a smooth version, and it's smooth because of the kind of resolution of the data used to infer it. And we're going to basically grow ice sheets of different widths, HW, and then just collapse them, and then watch the Earth rebound and measure that kind of relaxation timescale by fitting an exponential decay. And so just to show you how this works, we choose an HW, we grow the ice sheet, and we let it go, and we measure tau r. And we'll do it again for a different HW, and every time measure tau r, right? And so this is kind of what I'm doing. I'm considering the Earth in a very simple case. We've got a chosen viscosity profile, and we're just actually growing an ice sheet along the equator, it seems. This just made the math very simple. Okay, and so what slide am I on here? Okay. And so by doing that, we fit this kind of time scale. And so remember that the time scale of relaxation depends on eta over k. And so we tested 2 viscosity profiles, one that increases with depth and one that's isoviscous, right? And so there's no surprise, given that this is, if the time scale is dictated by this ratio, that the isoviscous mantle basically yields a tau R that's essentially constant with larger ice sheets. And the other profile has a tau R that increases by at least a factor of 2, roughly, a little bit more than that. Okay. And so how does varying this time scale of relaxation actually fit into the story of the transition? So I'm not a climate scientist, and so I don't have a coupled ice sheet model to use. And so I turned to a very classic study by Marsh and Saltzman, and the two developed a highly parameterized climate model that, tries to emulate all the feedbacks within the cryosphere, the atmosphere, and the ocean. And they postulated that the early and the late Pleistocene just represent two distinct solutions in this dynamical model that they have. And if you force this system and slowly vary arbitrarily certain control parameters in this dynamical system, they reproduce a flip between some sort of 40,000 year dominant to 100,000 year dominant ice age state. And they don't actually propose what that kind of arbitrary change, that secular change is. All they say is that, they have this line in the closing of the abstract. We assume that a slow progressive change in the model parameters associated with an as yet unidentified change in the tectonically forced equilibrium of the system could be the cause of the mid-Pleistocene transition. And so all we're asking is, we're going to use this framework to test our idea. Could changing tau R be, or at least contribute to, this unidentified change in tectonics? And so here are those coupled equations, and they're simple enough that, we can walk through them just to give us all some intuition. And so the rate of change of ice mass in the northern hemisphere is dependent on several terms. A represents some mean climate state. So this is always going to be there. This term is basically the decay of ice and captures the timescale of ice flow within the ice sheet itself. This term is an interesting one. It's a function to account for calving. So basically, we have the Arctic Ocean on one side of the Laurentide ice sheet. Once that Laurentide ice sheet hits the Arctic Ocean, it's going to be inundated with warm ocean water, and that's going to rapidly enhance melt at the margins of this ice sheet. And so this is dependent on the ice mass, and also B, which is basically the bedrock, right? So if we're going to sink, we're going to allow more waters to inundate, right? So this isn't a function that accounts for that. It basically enhances melt if the ice sheet hits the Arctic Ocean. And then we have our Milankovitch forcing. And so this is coupled to the bedrock subsidence. So again, how much we subside depends on the ice mass itself. Actually, it's the ice height in this equation. So there's this strange mapping. And also, it's proportional to the substance itself, and importantly, this bedrock relaxation time scale. And so all we're going to do is model this not so very complicated system, but we'll adjust tau R as the ice mass changes, right? So we've basically got this function of how changing the width of an ice sheet changes tau R. And so we're just going to, as we evolve evolve tau R accordingly. And so a key ingredient that I've kind of brushed past is the secular change across the Pleistocene. So we need something to drive larger ice sheets, right? And so it's somewhat established that over the Pleistocene, we've just been cooling steadily. And so what we're going to do that is just fit a linear trend to this. And we're just going to change this background state. And so in the original Marsh and Saltzman papers, they actually have mappings of different CO2 atmospheric content to this A0 term. Okay. And again, as the ice mass gets bigger, we'll just adjust tau R. And so here are results, just to kind of orientate you. Here are the oxygen isotopes. These aren't modeled. This is just for comparison. This is the forcing term. Here we're going to look at the different relaxation times, and this is the ice mass. So this is what we want to reproduce and hope looks like those kind of 40,000 to 100,000 year cycles. Yeah, that's what we're looking for. Okay, and so we'll start off with the isoviscous mantle, so the mantle in which viscosity doesn't vary with depth, and just look at what modeling this does. And so if you suffer from epilepsy or something like that, or just don't like jitter, focus on this one because they're a bit jittery, and I don't know how to change that because I don't know how to make these graphics very well. But here we go. We're just kind of forcing this system over 2.5 million years, and we get the ice ages. But as you see, the ice ages do get bigger because we're cooling down the climate in that A0 term. But nothing's happening to the periodicity. Still forced by obliquity, which makes sense because the obliquity is something that has power in the insulation. And so what about if we do the same experiment with the non-isoviscous mantle? So again, what we get is an increase in that relaxation timescale that's required because of the size of the ice sheets. And suddenly what you get is this flip to the different state where we have these much slower ice sheets. And this again is reproducing what those first studies I showed you, Abiuchi, and that reproduce these 100,000 years. The difference is that we're going back in time and showing that actually the same process, if you account for a non-isoviscous mantle, can actually produce this flip as well. And so we actually did this many times, of course, and the transition occurs for all of them. It's the timing that shifts, but all of this is to say is that just changing the relaxation timescale does flip you from one solution space to another. And so just to kind of emphasize this point, here's the power spectra of all of these records from the early, so this part of the time series. What you see is this dark gray line. Here's the eccentricity, the obliquity, and the precession. What you see is that it's dominated in the obliquity cycle, which is what we expected. And so is the ice and the oxygen isotope record. But if we move to the late cycles, that isoviscous line, so this yellow line, the peak remains at the obliquity cycle, except that the blue line falls in line with what we see in the oxygen isotope record, and so moves to this kind of low frequency eccentricity cycle. Okay, I'm okay on time. I've only got a few more slides. So the final conundrum, it's more of a speculation because I've not really explored this idea, but I do believe that increasing tau R has the potential to also increase the asymmetry in the growth and decline patterns. So as I said earlier, larger ice sheets are associated with longer relaxation times, and that is the fact that's key in producing those enhanced ice melt rates, which is what's observed in that kind of sort of slow growth, rapid decline. So smaller ice sheets, on the other hand, shorter relaxation times. Rebound is just, subsidence is just as fast as rebound, and rebound is just as fast as subsidence, right? And so this also could play a role in that asymmetry. And so I actually showed you a simplified schematic before. Actually, what's more the case in the Northern Hemisphere because of the Canadian Shield and the craton underneath it is actually we have a really thick lithosphere in North America. And so thick lithospheres behave elastically. And so small ice sheets might not actually have that much delay at all because they're deforming elastically. Okay, and so to summarize those three conundrums, I explained how previous authors found GIA, glacial isostatic adjustment, to be crucial in producing these kind of 100,000-year ice age cycles. But what I've suggested is that accounting for how the relaxation time changes with ice sheet mass or length scale might play a role in both of these other parts of Pleistocene ice ages. And so now going back full circle, is there any evidence for this, or must I wait like Milankovitch? Would be a little bit morbid if I had to do that. So we turn to Sweden now. Here are some images of across Sweden's landscape, where Sweden has been, just like many parts of North America, has been really shaped by these past ice sheets. So here's an esker in Angermanland, for example, in Sweden. But more specifically, there's this beautiful stretch of strand lines. So these are paleo shorelines that mark the retreat of the Fennoscandian ice sheet. And so there's this classic study by McConnell who explored this data set that was really like a really tedious kind of accumulation and collection compiled by Saramo in the 50s actually. And so here's that paper. I think you're getting an idea. I like reading old papers for some reason. But here's the transect of those strand lines. And here's their kind of elevation history with time. So I might not be able to make it out, but that's Angermanland. That was the figure on the left I showed you before. And what you see again is elevation histories across these strand lines. And the clever thing that McConnell did was that McConnell related this he analyzed this in a spectral way, so that he took into account time scales of uplift and length scales of what the ice sheet that would have been there had to be. And so what I'm showing you are his results, but this is kind of a later study where they revised the dating of these shorelines by Wizakowski. I still can't pronounce his name. But ultimately what you see in her work and McConnell's work is that relaxation timescale decreases with shorter wavelengths or higher spherical harmonic degrees. But all that's to say is that it's exactly what we expect. Shorter wavelengths will have shorter relaxation timescales. And so there is evidence, I guess. I'm like, looking, what was the point of the slide? Oh yeah, is there evidence? Yes, there is. And so hopefully I've convinced you that at least the variation of relaxation timescale is worth a closer look at within the context of these Pleistocene ice ages. The next steps is to really put this to the test. I've only used a very simple ice sheet model and very simple geometries to test it as simple secular trend. And, you know, we embedded these in the work of Marsh and Saltzman and Verbitsky, just to demonstrate the feasibility of this idea. Conversely, these kind of coupled climate ice sheet models that do have the machinery to consider the climate system more accurately and completely used a very simplified version of the solid Earth. The solid Earth is so much more than a single Greek letter. And so I do think perhaps we do want to consider incorporating a more comprehensive view of Earth's rebound dynamics in these models in order to kind of like, you know, fully account for all the possible potential feedbacks that are in play that control our long-term climate. And so, yeah, I'll leave it at that. Thank you for listening. I've listed a few acknowledgements here, but 1:22, are there time for a few questions? Okay, great, thank you.
Yeah, questions for Harriet, and maybe we can start with
Okay, yeah, so thanks for the great talk. So can you go back to the animation of the simple kind of climate model? Yeah, this one, yeah. So in the third plot, right, I think you showed before, like the relaxation time should vary with ice thickness, ice width, right? So this is vary with time, right?
Yes.
So I just wondering why is that? Because vary with time, it should be like up and down, something like that, right? The relaxation time for the blue line here.
Ah, I see what you mean. Okay, yeah.
Yeah, because ice width should vary with time instead of like that.
So yeah, so I see what you mean. So what I've done in that coupling is I've taken the kind of the peak growth because that's what will really matter is the peak of each of these.
Oh, okay.
I should
peak.
have clarified that. But that's a good point because yeah, if you look at this should go crazy. Yeah,
Okay.
so it really again is the growth and that peak point. That's what dictates.
At the peak point. Oh, yeah.
I should make that clearer. But that's a really good
Why the peak is going up?
right. So first it starts out because the ice sheets are really small. It's not very clear here, but you actually get rapid kind of increase in tower because of the slope of tower. It's very sensitive at the start.
The ice is larger and larger.
Exactly. So that peak grows, and actually it slows down the increase because basically you get ice sheets that grow so much that actually the deformation starts bottoming out in the deep mantle, and so you actually don't get too many changes. And so there's a little bit of memory in this also. So past ice ages are also affecting the rebound of future ice ages. You're not quite fully recovering because like today, we're still rebounding. So there's a little bit of that at play also.
We'll talk later, but does this going from like stage 5A into stage 4 and 3, that's a rather sharp initial. Would that kind of play into first building on the lithosphere and deforming that allowed you to grow large very
Potentially.
quickly? And
Potentially.
then you tapped into
Yeah,
the
I
deeper-
feel, looking at the individual stages, I feel like I'd want to like model that. How big are the changes between 5A and 5? Yeah, this
5A to 4.
5A to 4.
it's like a different language.
Yeah, 30, 50 maybe.
50 meters. The first big step
Yeah, right,
into the last is about half of it.
I'd like to model that specifically, right? That'd be really interesting, guys. But I don't know. I imagine so because people do consider when they do this type of GIA modeling, do consider thicker lithospheres for these regions.
And slightly different. We've been doing this 2.5 million years with 8 big ones. Does it ever weaken the upper mantle? I mean, like, I think of a stream
This is a
will
really
get sprung
interesting.
eventually.
So I guess like what you're getting to is kind of by pounding the earth with ice, are you actually causing the viscosity to decrease because you're weakening the rock, which is like kind of non-linear rheology, non-linear deformation, which is way too complicated for someone like me. But it is interesting. It is something I've thought about. You know, prior to the nucleation of the Laurentide ice sheet, we've had a continent that's just sat there for ages, and so it's cold. So unlike kind of hot rock that is low in viscosity, it's cold. It's strong, and so suddenly you start growing ice, and you're kind of slowly pounding, and these ice ages are getting bigger and bigger. Are you weakening that rock, and what does that do in return? I don't know. Also, those laws, those kind of constitutive laws that describe how stress maps to strain, for these cases are really, really unknown. We just don't have the experiments to tell us exactly how rocks should behave under these circumstances. Because it would add hysteresis to this problem. That's really cool.
We could talk about this later, but I mean, this isn't the only 100K ice world. I mean, there was a 100K ice world in the Miocene. And it's interesting to apply this approach to looking at early Antarctic ice evolution. It shuts off at 12.8 when the ice sheet becomes quasi-permanent.
Right.
But there was a strong 100K signal back then too.
I didn't know. Okay, that'd be and Antarctica is very interesting because half of it is under the very low viscosity. The Western Antarctic is very low viscosity, and then
If this would be an East Antarctic model,
right.
Because really the
which
main
is thick and a bit more like North America in that regard.
Okay.
Very nice talk. I was wondering, so I guess I had two questions. So one is I was confused about how you were treating the elastic thickness of the lithosphere, because if you have a shorter wavelength, long spherical harmonic degree, stress, I mean, it's all compensated by the elastic lithosphere, right? So then how much does the viscosity or viscosity contrast play a role at all? And second question is, when you're doing these sort of flexure study and you do have a flexure and there's some time for the relaxation to bound back, you're effectively changing the radius of the planet as well. So does that change the moment of inertia of the planet, leading to changes in the rotation rate of the planet itself?
Okay, yeah, no, really interesting. So the first question was, we have an elastic plate, and you're saying that that should accommodate all the stress, is that right?
Yeah, I mean, so if there's
Interesting.
very little heat flow at the elastic thickness of the lithosphere is like, let's say 500 kilometers, then all of that stress can be accommodated by the elastic thickness of the lithosphere.
Right. But I guess the elastic thickness of the sphere, I'm considering is much more like kind of 100 kilometers, right? 500 kilometers is pretty thick. I'm not sure.
I work primarily on Mars, and there we have
Oh,
500. Yeah,
I
so
see that. That's it. So yeah. So in this circumstance, a lot of deformation penetrates right through the mantle on ice sheets. So these ice sheets, I mean, the peak of the Laurentide ice sheet is about 4 kilometers thick, a few thousand kilometers. It got down to like, I'm going to be embarrassed. What did it get down to? It got down to Long Island, definitely. That's the. So definitely increases flow throughout the mantle, and the lithosphere, you get this peripheral bulge, right? And that bulge is partially, where the bulge is because of the flexural characteristics of the plate, but also the mantle flowing underneath it to fill that void. The second question, yeah, this kind of stuff does induce changes in moments of inertia, for sure. Because if you grow an ice sheet off the rotation axis, you're going to change the moment of inertia. So GIA, I don't do that in this calculation at all, because you saw the little I literally just figure out what tau r is and then just put it into this thing, which has no idea. It is a 0D, 1D coupled set of equations, but GIA itself, changes in rotation are like a very big part of what we model in GIA as well. Because shifting mass across the planet will change change moment of inertia, and drive through polar wonder, these sorts of things also.
Thanks, that was really interesting. We're following the thread of sort of, can understanding the mantle help us understand the glacial cycle that we see in the tempo? I was wondering, given that there's still substantial uncertainty in mantle viscosity structure, can you follow the thread in the other direction to actually use your observed climate variations to rule in or rule out the
Oh yeah,
viscosity
yeah.
structure?
So I guess a lot of viscosity structure does come from observations of uplift. So that's one answer to that question, but kind of, I feel like you're getting a more broader, deeper kind of question, or maybe I'm giving you more credit. But
Yeah, I'll take it.
So GIA data is one of the key constraints on mantle viscosity. But in what you're saying is, can we kind of think about other or I think yes, definitely to rule stuff out and rule stuff in.
I guess what I was wondering is, beyond using like the GIA data, like you showed this paleo shoreline.
Yeah.
If you see transitions in when you have the change of 1,000 year to 40,000 year specific, would you say attribute that to
Yeah. No, that
structure?
I think there are just too many other facts, and I've come to learn this more delving into the literature, that there's a lot of stuff. I've definitely simplified this story a lot. There are a lot of complications. In oxygen, there's also temperature in this signal, and there's more work that's coming out, and it's not published work, it's just work I've spoken to a lot of paleoclimate people who are like, a lot of the signal is actually temperature, and less of it is ice now. So there is a lot to this that I'm not understanding, and a lot to the switch from 40 to 100 that as I mentioned earlier, there are many different processes proposed. But if this process was the process that was the major factor, I think, yes, that there would be some way to kind of understand, like, some people think viscosity changes abruptly with depth. Does that mean that there's an abrupt transition? And there's reason to believe that, rocks behave differently and they switch at certain pressure temperature conditions, phase transit. There are reasons to believe that abrupt things could happen, and does that result in an abrupt transition? So yeah, exactly. Those sorts of things, I think, are very interesting things to explore. If this convinced you that this was the driver, which I'm not convinced myself yet. So
Thank you.